Alright, what's up everyone? Welcome back to our C math library. Today we're going to be doing some more matrix stuff. I know I apologize for skipping or missing out on the big integer stuff, but we will get back to that. I just wanted to do this one quick operation, and then we should be pretty much done with matrices for a little bit, and then we'll get back into big integers in the next video. But today we're going to be looking at matrix inverses and how to find them procedurally, and then we're going to look at two methods, but we will only implement one of them because one and the other just makes the other's inefficient, so it would be pointless to implement. But you could with the methods or the functions that we already have here. So let me go to the desktop. Okay, so in a linear algebra class, the first way you might learn to take the inverse of a matrix, which by the way is just bag fell. Oh. So you know how inverse of a number, so x times 1 over x is equal to 1. Or x times x to the negative 1 is equal to 1. Well, with matrices, you can't really divide or do 1 divided by a matrix. So instead, if you have A, which is n by n, and it has to be a square matrix, that's required, then you have A times A to the negative 1. So A inverse is equal to the identity matrix. So it's kind of the translation into matrix algebra of these two concepts here. And it turns out there are two ways. So we'll look at the more introductory way, which is doing Gaussian elimination, so with reduced echelon form, or row reduced echelon form, in fact. The first way is if you just take the matrix and then you augment it by the identity matrix, and then you perform Gaussian elimination, which is, in this case, it's going to be RREF, that algorithm that we wrote, and you will get I, and then the identity matrix augmented by the inverse of the matrix. So this is actually relatively easy to implement with a bunch of functions that we have. We have the augment function, we have the row reduced echelon form, and then, but the only challenging thing would be to actually, or not challenging, but we don't have a function to take a matrix out. Like we don't have take this number of rows, take these rows and these columns. But that wouldn't be too difficult to implement. But anyway, yeah, this becomes a little more complicated with larger matrices, just because reduced row echelon form is somewhat inefficient if you're working with matrices that are pretty big. So this just makes more sense just to have another way to do it, and there is one actually. And it's done in 4 steps really. First one is to find the matrix of minors, and the matrix of minors is essentially the matrix. So the minor of A is equal to, I don't know if there's specific notation for this, but it's going to be the determinant of A without row I and column J. So essentially the minor of A I J is equal to the determinant, or the entry of this is going to be equal to the determinant of the minor matrix with where the minor matrix is just A without row I and column J. That's kind of, I think that's the notation. I could be wrong. But anyway, you get, so I mean, I'll just do one entry as an example. If we had 3 by 3, 1 1 1 2 1 3, oops, we can actually just do 1 through 9. Makes it easier. So the minor of this matrix would be equal to, in the top left entry would be the determinant of this matrix without the top row or the left column. So essentially it's going to be the determinant of 5, 6, 8, 9, and I'll just do the rest of this row as an example. And you have 4, 6, 7, 9, and then 4, 5, 7, 8. And then you just do the same thing for the rows below, except you just cut out the second and third row, respectively. So that's your matrix of minors. And then what happens with the matrix of minors is then we convert that into cofactor matrix. And it's essentially performing element-wise multiplication on two matrices, where one of the matrices is the cofactor matrix, and the other is the Sine matrix. And the Sine matrix is essentially just a matrix that has corresponding signs, and the signs just alternate. Just like that. And here, the Sine matrix, so you just go left to right, top to the bottom, and you just alternate signs. Wait, is this right? It essentially makes a checkerboard of signs, and if it was a 2 by 2, it would still just be plus minus, then plus, oh no, plus minus minus plus. So you start each row with alternating signs, then you go right from the row, like that, and you get, I'll just do the first entry now. So this is plus 5, 6, 8, 9, and then minus dot dot dot. And do that for all the entries. Now it's our cofactor matrix. Now from the cofactor matrix, we find an adjugate. God, this is actually giving me PTSD right now. The adjugate is the transpose of this matrix, and we have a function to find that, which is is equal to the cofactor matrix transposed. That gives us some matrix, and then finally the inverse of matrix M is equal to 1 over the determinant of M times the adjugate of M. I did not prove this, and I completely forget how to prove it, but it does it somehow, and it turns out this is much more more efficient than doing the reduced row echelon form, especially for larger matrices. And then what happens now is this gives rise to the concept of invertibility. So what makes a matrix invertible? Well, first of all, it has to be square. That's just a given. But also the determinant cannot equal 0, because if it is 0, we have 1 divided by 0, which is invalid. So this is just a law of matrices. So a matrix is invertible if and only if its determinant is non-zero. So yeah, that's my little spiel. I don't really want to do an example, just because it would just be annoying. But anyway, let's go ahead and try and implement this. Open up Visual Studio Code. Okay. we will start off with the function. Alright, so we're going to have our first function is going to be the cofactor function. So we're just going to have a function to determine the cofactor of a matrix at a specific entry. Float cofactor, pass in a matrix M, and an unsigned int R and unsigned int C. And then for this, I'm just going to do all the definitions at once, and then we can write them all, or define them all, or write the bodies of all of them. So that's our cofactor. Then we're going to have a method returning a matrix called the Cofactor Matrix, and you just take in a matrix pointer M. Then another returning matrix called the Adjugate. This will just find the adjugate. Then we'll have a method that returns Boolean, and it will be called Invertible, and you'll just pass in a matrix pointer M, and this will determine if the matrix is invertible. And then returning matrix, just call it inverseMat, and pass in a matrix pointer M. So these are the 5 functions that we will implement today, and they just essentially go through the steps of what we just outlined. Alright, so I'm going to copy all the definitions. God, I have to scroll through 1,000 lines to find this. Here we go. Okay. Oops. Start with the cofactor. So our general condition for all these methods actually is going to be it must be a square matrix with at least one row. Ooh, I didn't even turn the music on. Let me turn this on. It's quiet. So yeah, this is going to be a condition that will be shared by all of these methods. So if m.rows does not equal m.calls, or m.rows is equal to 0, return 0.0 floats. Then once again, the row, the parameters will count from 1, so we want to subtract 1, r minus minus and c minus minus. Then we also want to have a boundary check. So if r is greater than m.rows, or c is greater than m.calls, return. We can actually just put this in the condition above. So since we're putting this one above here before, turn this down a little more. Since we're putting this before the where we decrement it, we have to say or r is greater than or equal to m.rows, or c is greater than or equal to m.calls. So if any of those 4 conditions pass, return 0. Now we're going to determine alternating signs. We're not going to have a function to really find the matrix of minors, because you don't really use it for anything. You really just care about the cofactor matrix mainly. So we have to incorporate the alternating signs here. And it turns out that if row plus column is even, it's positive. And if row plus column is odd, it's negative. And that's just something that arises out of the alternation. So we'll have a character, sine is equal to ternary operator here, r plus c in parentheses, then bitwise and that with 1. This is just a quick trick to figure out if something is odd or even. And if this is equal to 0, it's going to be even, and otherwise it's going to be odd. So question mark 1 colon negative 1. The reason why the bitwise and with 1 works is because the only thing that will make a binary number odd is if it has a 1 in the 2 to the 0 place. because that's the only place for it to be odd. So therefore, if you bitwise AND it with just a 1, which is just a 1 in the 2 to the 0 place, that will get you the bit in the 2 to the 0 place. And if that equals 0, then then it's odd, otherwise it's even. Or if it gets you a 0, it's even, otherwise it's odd. Okay, here we can't just call determinant and exclude the current row and column, because that's not how this determinant function is written. So in fact, we do have to create our own spliced matrix, but we have a function for that. So mat spliced mat is equal to the function splice mat. Pass in a reference to m, and the exclusion row and column will be r+1 and c+1. You know, we don't even need to decrease r and c, because it doesn't really matter. So if you don't decrement r and c, you can just say r, comma c. Yeah. So that's your spliced matrix, and then the cofactor will be equal to the sine times the determinant of the minor matrix, or the determinant of the matrix without a row and column. So float ret is equal to sine times determinant exclusion. Determinant. And then we just pass in a reference to spliced mat. And then once we're done here, since we are not returning spliced mat, we want to free the matrix, so free mat, and then pass in a reference to spliced mat, and then return ret. The reason why we haven't called free mat before is because if we create a helper matrix, it's usually going to be returned, but here it's not going to be returned, so we do have to free it explicitly. I feel like I just drank fucking lead. That water did not taste right. Okay. Now for the cofactor matrix, we're essentially going to be just looping through the entries and creating and just taking the cofactors at each entry, or for each position. Once again, same condition, so must be a square matrix with at least one row. So if m.rows does not equal m.calls, or m.rows is equal to 0, then return mat undefined. Now we're going to actually allocate a matrix because we don't want to modify this matrix, we want to just create a new one. So mat.ret is equal to allocate mat, and it has the same dimensions, so m.rows for rows and m.calls for calls. Now we're essentially going to iterate through each element. So for unsigned int r is equal to 0, r is less than ret.rows, r++. For unsigned int c is equal to 0, c is less than ret.calls, c++. And then ret.elements at r at c is going to be equal to the cofactor, so we're calling the cofactor function, passing in the matrix M, and then the row and column to cancel will be r+1 and c+1. And then after this we can return ret. I'm actually gonna fix or rewrite this up here, just because it makes more logical sense to separate the if conditions in the cofactor function. Alright, so that's our cofactor matrix function. Pretty simple. And now for the adjugate, you may think that the logical way to do this would be to simply call the cofactor matrix function and then call the transpose function. But it turns out that that would just be inefficient because you're essentially iterating through each element twice, whereas if we just kind of do the transpose within the assignment, it'll do the same thing. So we'll start it off with the same condition. So you can actually just copy the condition from cofactor matrix. It must be a square matrix with at least one row again. And then we're going to allocate a matrix. Same way, mat.ret is equal to allocate mat, pass an m.rows and m.calls. And then we're going to do the same loop for unsigned int r is equal to 0, r is less than ret.rows, r++. And for unsigned int c is equal to 0, c is less than ret.calls, c++. Then ret.elements at r at c is equal to the cofactor, pass an m, and since we're taking the transpose, we're just going to swap the column and the row. So c+1 and then r+1. So when calling the cofactor matrix or the cofactor function, we pass in the column +1 for the row and row +1 for the column. Just because once again we're taking the transpose. And then after the loop you can just return ret. So these two functions look almost exactly the same, except it's just the call and the parameters here that make the difference. Okay, now for invertible, it's going to be a simple call to the determinant function, and then we will determine if the determinant, or we will just set it equal, or we will do a Boolean operator to determine, there's no other word to say it. We're going to determine if the determinant is 0, and if it is, it's not invertible, otherwise it is invertible. So it just return determinant, pass an m as the matrix is equal to 0, or is not equal to 0. Or, we can actually just simplify this and say if it's not a square matrix. So if, same condition actually. So must be a square matrix with at least one row. Oh, I'm just... I tried to go away from the microphone because I knew that would have blown the shit out of any headphone wearers. Oh, that was Jesus. Okay. Jesus. Okay, yeah, same condition. It must be a square matrix with at least one row, and if it's not, return false. And then otherwise, we're going to return the determinant is not equal to 0. I'm really hoping that was I was far away enough from the microphone. Oh, give me, let me blow my nose. Give me a second. Alright, my ear is still plugged, but we'll have to get through it. Okay, yeah, for inverse mat, you might think that the precondition would just be to call invertible. However, this would be inefficient because, as it says in the formula here, we're going to need the determinant, actually. So we will essentially perform the same condition checking just in the function here. So we'll have the first condition being the exact same. So if it's not a square matrix with at least one row, then just return mat undefined. And then now we're going to get the determinant. So float det is equal to determinant, and pass in the matrix M. And if determinant is equal to 0.0 float, return mat undefined as well. And now we're just going to use the formula. The inverse is equal to 1 over the determinant times the adjugate. So mat.RREF is equal to the adjugate M, then mat scalar multiplication by. That's a function that we wrote that directly multiplies the elements of a matrix, so we have to pass in a pointer here. Pass in a reference to ret, and then the scalar will be 1.0 float divided by the determinant, and then we can return ret. Alright, that's fun. Alright, let's try this out. I think that's pretty much it. Alright, let's use an example. Yeah, so this here is the first method I talked about by doing Gaussian elimination to actually figure out the inverse. Alright, let's do this one. So 4, 7, 2, 6. Start off with a simple example. So 2, 2. 4.0, 7.0, 2.0, 6.0. Alright, and then we'll say mat inverse is equal to the inverse mat, pass in a reference to M, and then we will print the matrix, the inverse. Let's run it. Oops. Okay, didn't like a few things here. Oh, okay. Alright, so I just what function is this? Cofactor. Alright, so in the cofactor function, I called the function splice matrix, and then I pass in a reference to M, but M is already a pointer, so it was passing in a pointer to a pointer. So just pass in M there. So when you call splice mat, it should just be MRC as the parameters. Alright, let's clear the screen, and now let's try running again. Nope, it didn't like it again. Splice or free is free not a function? Or free mat? Did I not make this a function? I guess I did not make this a function. Okay, well. Yeah, this is another function that we have to have. Void free mat. Pass in a matrix pointer M. Just make sure you define that in the header. I would do it near the top, so it's noticeable. Let me actually just find this. Huh. Yeah, I guess I never... Yeah, I guess I never did that. Alright, and then you can just define this. And all we're going to say is in the function, we'll call free the system function, and then pass an m.elements. Then m.elements is equal to null, m.rows is equal to 0, m.columns is equal to 0, and then free m. Alright, so we free the elements, then set the values to 0. This isn't really necessary, I just put it there. And then you free the pointer at m. Alright, now this should run. Alright, that's not right. Let's look here. All right, let's use this example. Ooh, this is really... All right, let's first go into main. And I'm just going to print out the cofactor matrix and then the adjugate too. So print mat cofactor matrix m. Okay. That's definitely not right. Let's see. There's something wrong in the cofactor matrix function. I'll check my reference to see if anything's wrong. Alright, I think the cofactor matrix is fine, so I think it might be the cofactor function. All right, I'm going to print out the spliced matrix, so everyone that it gets. So we gotta... what the fuck? That doesn't make any sense. Alright, let me debug this, I guess. And I'll break at line 1095. Run next. Print ret.rows. 2. Print ret.calls. 2. Alright, in here. R is 1. Print C is 1 as well. That's good. Print sine should be 1. Good. Now print the spliced matrix. That's good. Or wait, is that good? Yes, that is good. Alright, and then free that. Or print red actually. 6, good. Print red.elements. Add 0, 6, good. Alright, R is 1, C is 2. Oh, okay, yeah. I had the boundary condition wrong here. If R is greater than m.rows or C is greater than m.calls in the cofactor function, make sure it's greater than. I think I explicitly said make it greater than or equal to, but that was wrong. It should just be greater than. If we subtracted 1, then it would have to be greater than or equal to, but we didn't, so. Alright, let's run this, and we get a 0.6, negative 0.7, negative 0.2, 0.4, perfect. Alright, let's try a larger one. Three, 1.0, 2.0, 3.0, 0.0, 4.0, 5.0, 1.0, 0.0, 6.0. Clear the screen and run. Oh, why? I don't know what these why the fuck are these fractions here? Alright, let me actually multiply this by 22 to see if that gets me anything. So print mat scalar multiplication, the inverse, and then I'll say 22.0 float as the factor. So that will give me 2 integer values. We got 24, negative 12, negative 2, 5, 3, negative 5, negative 4, 2, 4. Perfect. You'll love to see it. Yeah, alright, that's good. Oh yeah, so that's inverses, and there's actually one cool thing that we can do with this, and that involves determinants. So when we did determinants, we expanded across the rows here. So let me get my tablet out once again. Alright, so the determinant of a matrix, let's just say that we expanded across the first row. So this is going to equal to the sum, I goes from 1 to n, and it's going to be this negative 1 to the I plus 1. And this is synonymous to, or let's make this j actually. The counter, I'm going to make the counter j because we're going to be iterating through columns. So j is equal to 1. So 1 plus j, and this is synonymous to I plus j because I is 1. This times the matrix element at ij times the determinant of the matrix without I and j. And what is this really? That's the minor matrix, right? And then what is this here? This is the corresponding entry in the Sine Matrix. And this is just the element in the matrix. So this is essentially equal to the sum j goes from 1 to n of the cofactors of 1j. Or not the cofactors, but the cofactor of 1j times the matrix element at ij. Because the sine times the determinant of the minor matrix is, do I even put that anywhere? Yeah, it's the element-wise multiplication. So C at ij is equal to the Sine matrix at ij times the determinant of the minor matrix ij. So we're just going to translate that over here, which will give us another way to find the determinant of a matrix. But once again, this is not as efficient because you're still splicing the matrix. You're still going to be making n new matrices for one for each element in the row. So we'll have a new function here called determinant. It just seems like we have 5 of them. I'm actually going to rename the existing function that is called Determinant Exclusion, and I'm going to put an underscore in front of that. And then the function that has determinant, I will call Determinant Exclusion. And then we'll have a float determinant and pass in a matrix pointer m. Now for this function, it's going to be pretty straightforward. Once again, same conditions. It must be a square matrix with at least one row. I'm just going to rename, since I renamed the determinant exclusion methods, I'm just going to update that to include the underscore in the recursive call. And I will also make any existing calls to determinant called determinant exclusion. Don't think there are many though. Determinant exclusion. Okay, now for the determinant function that we're going to write. It's going to have the same condition, so it must be a square matrix with at least one row. And then we're going to have a float ret is equal to 0.0 float. And then we'll expand across the first row. So for unsigned int c is equal to 0, c is less than m dot calls, c++. If m dot elements, oops, changed my language for some reason. If m dot elements at 0 at c does not equal 0, we will add the cofactor times the element. So ret plus equals m dot elements at 0 at c times the cofactor, passing in m, and then the row is 1 and the column is c plus 1. And at the end, just return ret. And you know, we could actually... I'm just thinking about something here. In the inverse function, since we already call that... Ooh, this might be good. Since the adjugate holds the transpose of the cofactor matrix, we could expand across, or we could go across either of the rows and multiply them by their corresponding elements in the transpose of the matrix, and that would be our determinant, would it not? Alright, let's try this out. So we will take the adjugate, and we'll call that at the beginning. Right there. And then we'll have our float det is equal to 0.0 float. And then expand across first row. And since we already did all these computations, there's no need to calculate the determinants twice. We can just use this. So we'll expand across the first column, actually, or first row of the matrix. So for unsigned int c is equal to 0, c is less than m dot calls c++. If m dot elements at r at 0 at c does not equal 0.0 float, we're gonna say det plus equals m dot elements at 0 at c times the adjugate's value, adjugate dot, or ret dot, or let's actually call this adj. Or wait, no, we'll call the matrix adj. So mat adj is equal to the adjugate, then float det is equal to 0, and then in the loop, if the element is not equal to 0, we're going to multiply the element by the adjugate's value. So adjugate dot elements at c at 0. And we're doing c at 0 because the adjugate is the transpose. And now, this should give us the same results. Oh, it didn't like it. Where is this? 999? Oh, yeah, okay. So because I renamed the determinant exclusion method, I called it incorrectly. So just make sure you call the proper method. The determinant exclusion without the underscore takes in only the matrix, and that's the starting method. And then with the underscore actually takes in the lists. We got 24, negative 12. That looks right. Let me just make sure. 24, negative 12, negative 2, 5, 3, negative 5, negative 4, 2, 4. Awesome. Alright, so that's a little thing, I guess you could say. I just created another matrix here to actually separate the adjugate from the return, because just for naming purposes, to make the code clearer. Okay, so that's pretty cool. Little efficiency boost. Once again, the reason why we're doing this in here instead of calling the method is because we already calculate the cofactor matrix. And if we can use the cofactors to calculate the determinant, why not just use that matrix in this function? It just makes it a little easier. All right. I think that's pretty much everything I wanted to do. I'm recording this right now, but this will be out at some point. I don't know when, but when it is, don't hesitate to ask questions in the comments and shit. But I hope you guys enjoyed. Hope you learned a few things. I know it's probably a little difficult to follow along with the videos, or with these videos, because this file has over 1.1 thousand lines, and I'm just scrolling through it constantly. But I'm trying to keep everything keep you guys noted of which function I'm in. But I probably should break this up at some point. But I mean, it's all matrix. Yeah. But anyway, yeah. Alright, hope you guys enjoyed, and when we return to this library, we will be doing the big integer once again, so that'll be fun. So yeah, until then, have a good one, keep yourself safe, happy holidays, and don't spread any germs at holiday dinners. And I'll see you then. Have a good one.